This session, we have Juan Perdomo, and then later on, Moritz Hart giving talks. So the first talk is difficult lessons on social prediction from Wisconsin public schools. Thanks.
Great. Thank you so much, Nika. So today I'll be talking about some joint work with Talani Britton, Moritz Hart, and Reddy Abibi on difficult lessons on social prediction from Wisconsin public schools. And I want to start out by thanking Carl Frederick and Justin Meyer at the Wisconsin Department of Public Instruction. Without them, we wouldn't have been able to do this project. So the topic for today's talk is we're going to be evaluating individual risk predictors that are used in US public education. Particularly, we can talk about early warning systems. And the question we're going to try to answer is, does this really popular class of risk predictors improve educational outcomes? And by educational outcomes, I mean high school graduation rates in US public schools. Great. So early warning systems, the first pilot started around 2007, and they very quickly boomed. So according to a survey by the US Federal Department of Education, over half of US public schools had implemented some version of an early warning system by 2015. And the main question these early warning systems try to answer is, will a particular student graduate on time from high school? So they use features from students in middle school and they make a prediction as to whether this student will graduate from high school in 4 years. So like within the standard timeline. Right. And the thesis behind these early warning systems is that they're meant to improve graduation rates. So I've kind of highlighted the main pipeline here in 3 stages. So the first step behind early warning systems is this early identification step. So typically, they make predictions on the population of students sometime around 8th grade or like before high school. And the main output of the system at this point is like a set of high risk flags. Like these are the students we think are unlikely to graduate from high school on time. And these flags are used by data teams and counselors within schools to target interventions to students that they believe need help, with the idea of increasing the number of students that graduate on time from high school. The question we're going to try to answer today is this thesis really true? Like, just to what extent does this idea really map onto reality? Great. So in particular, we're looking at the Wisconsin DEWS program, so dropout early warning system. And this is an early warning system that was implemented by the Department of Public Instruction starting in 2012, and it's used statewide. So it makes predictions on every single student in Wisconsin public schools, particularly from 5th to 8th grade. So we're talking over 200,000 students each year. The system, it has 2 main outputs. So the first one is a DEWS label. So this is like a holistic evaluation of how likely does the DPI think that a particular student will graduate from high school on time. So, and this is like, according to the action guide they published, this is like the main piece of actionable information that the system provides. So low being that there's a low risk of this student dropping out, and a high risk being that we really think this student should be intervened on immediately. In addition to the DEWS label, they output a score, which is really just like a probability of graduation. And these 2 quantities are related, as we'll literally see in the talk. In terms of implementation, they use things like random forest, classical like kind of machine learning methods for tabular data. And the models themselves use a pretty rich set of features. So they really do a good job of like collecting a lot of data around students that really describe both students and their communities. So in particular, I'll try to categorize this like large set of features into 2 broad classes. The first one is like individual features. These are quantities that describe individual students, like what was my test score on the standardized exam, how many days was I in school, even things like what is my gender, what is my race. And then there's things about students' communities, like what fraction of my school is non-white, what fraction of my school qualifies for free or reduced lunch. So these are not so much things about me as a student, but really describing the people around me. Okay. So something to keep in mind as we go along. So kind of going back to this thesis, early warning systems are really about targeting. I'm glad to go after Emily because this is at a high level something very similar to what's happening in the IRS problem. So targeting is, resources are scarce. Public schools, we can't intervene on every student, right? So we're faced with this difficult problem of trying to understand which students need the most help, right? So we're going to use prediction to try to answer this question: who needs the most help? So as computer scientists, we can think about these as just sorting algorithms, right? We take as input a population of students in public schools, and we output a ranked list of these students where the ranking is according to this dropout risk. So here, higher numbers means you're more likely to graduate from school on time. And the dropout risk serves as this like concrete proxy for an otherwise subjective notion of, how much do you need an intervention? Okay. So given this analogy that early warning systems are really just sorting algorithms, this is kind of like the evaluation framework that we're going to use. So an effective early warning system should do two things. First, it should prioritize students accurately, right? Students who are in higher need of an intervention or more likely to drop out should appear at the front of this list, whereas students who are generally doing well should appear further towards the back. And moreover, these predictions, they're made with the very explicit intent of changing outcomes. So the prediction that a student is high risk should hopefully be a self-negating prophecy. They should change outcomes. They should be performative, right? So if I predict that a particular student is at high risk versus I predict that a particular student is at low risk, this should hopefully change the likelihood that they graduate from high school on time. Any questions so far?
Do you just have one central warning system for the state, or is it just more like each schools have their own like model separately?
Great, yeah. So early warning systems across the US vary in implementation. The one I'm talking about today is implemented at the state level. So the State Department of Education generates predictions that are sent out to every school, every public school in the state.
Does the data that these models are trained on include whether students are intervened on?
No.
So relatedly, how do you measure this if you don't have a trust control?
We'll get into that.
So what are the features that are being sent to the warning system?
So they're pretty broad. There are a lot of like demographic information, like gender, race, things about like income, like does the student qualify for free reduced lunch? There's academic performance, whether the student has been subject to disciplinary history, and a lot of things about students' communities, like what fraction of the school is non-white, what's the how many students in the school qualify for free reduced lunch, things like that.
Can you say quickly again what year this prediction is based on?
So the system started in 2012 and it's been used up until now. The system makes predictions in 5th, 6th, 7th, and 8th. Today we'll be talking about mostly the 8th grade model. So I guess, yes, good question. The kind of the typical way this prediction is used is to triage students as they come into high school. So like when students change school, enter 9th grade, data teams or counselors look at the predictions to try to understand which students should be paying attention to. Great. So jumping straight into the findings, we find that these DEUCE predictions are actually very highly accurate. So like they provide a very good signal regarding which students will graduate from high school on time and which ones won't. Unfortunately, the system does not improve outcomes. All right, so there's no sense in which, or we find no evidence that this high level of predictive accuracy has translated into high graduation rates in Wisconsin. And we propose an explanation that's based on the role of environmental factors in this system, and I'll get into more detail exactly what I mean here. Great. So starting with the accuracy, DEUCE is quite good at prediction. So I mentioned there were two main outputs, right? The label and then the score. So we'll look at those separately. So starting with the score, amongst the group of students over the last 10 years that were predicted to be at low risk of dropping out from school, 97% of these students graduated. And amongst the students that were predicted to be at high risk, only 70% of those graduated. Moderate risk students, it's a relatively smaller bucket, only like 6% of students are assigned to this bucket, but it lies somewhere in between. And these gaps are pretty significant relative to the 90% graduation rate in Wisconsin public schools as a whole. So for context, 90% actually quite high for US schools, for US states. Moreover, we can look at the score. So I'm plotting the calibration curve for the predicted probability. So on the x-axis, this is the predicted probability of graduation. And then I'm bucketing students by their predicted probability and looking at, for a particular bucket, what fraction of those students graduated. So we see that as a whole, the score is miscalibrated, right? It should really lie on this like blue dotted line. But this miscalibration is relatively mild, right? Because we don't really care about what's the real number. We only care about these numbers in a relative sense. So like if I am more likely to drop out of school, then my number should be lower than for a student who is less likely to drop out of school. So as long as this like purple curve is like aligned with a positive slope, the score is good. Yeah.
This is after intervention, right?
Hold on to that. Yeah. Good. So from this sense, like going back to the sorting algorithm analogy, like the list that we're outputting is actually pretty well ranked, right? Like really students who do need more interventions appear at the beginning of the list.
I'm sorry, it's hard, you're saying high accuracy and high rank, but it's a bit difficult for you to see these numbers. Like, I mean, why is having the high bucket be 70% be considered a good accuracy?
Well, I guess, yeah. Relative to what?
Like 0%, right?
Yeah, relative to what? Yeah, good.
No, so 0% would be great.
Yeah, really
right?
great.
So why is 70% high accuracy?
I'm saying that this is like the graduation rate between bucket varies significantly between, well, I guess relative to the average graduation rate. So like these numbers really do mean qualitatively different things.
Yes. That means you're doing better than null prediction.
Better than
But
null prediction.
Doesn't say you're anywhere close to
Base optimality. Yeah.
Okay.
Yeah. But you know, it's a non-trivial signal of whether someone's going to drop out. Yeah. Good. Good. So, but ultimately these predictions are ineffective. So we find no evidence that these high-risk predictions lead to effective interventions. And here I'm trying to answer a counterfactual question, right? Like, what is the outcome of a particular student if I predict them to be at high risk versus at low risk? And I'm doing this based off observational data. So I better have some sort of experiment that happening. Why is it not calibrated?
Because the predictions are effective, so it's.
So yeah, I don't think the predictions are effective. I'll try to prove that to you now. So we can leverage a natural experiment. So particularly like the dues label is determined by thresholding a continuous score, right? So we predict this probability of graduation, and if it lies above an arbitrary threshold set by the department, a student is assigned to the high risk bucket, versus if it's below, you get put into moderate risk bucket. So you can try to estimate this treatment effect of what is the effect of assigning people different predictions via regression discontinuity design. Right? And this leverages the idea that like, if you look at students whose predicted probabilities lies very close to this threshold, you essentially have like a randomized experiment here. Okay. So we find that we ran this RDD, and then we find that this treatment effect of changing the prediction from moderate to high risk changes students' likelihood of graduation by less than 5%, but the resulting confidence interval covers 0. So you can't reject the hypothesis that this prediction has 0 effect. Yeah.
So, like, what about the students who it predicts to have like really low, like the ones that are very confident aren't going to graduate?
Yeah, like
so I could imagine like maybe the intervention works better on some populations than others.
Yeah, it's certainly possible that these predictions could have very different effects on different populations. Fortunately, we can't answer the question for the very, very bottom students because we don't have any kind of randomization there. Great. And then you can also look at this analogous comparison of trying to predict like what's the treatment effect of changing someone's label from low to moderate risk. And there you get an even smaller effect. So less than 3%. Good. So what we find is going back, yeah.
Do you know that the borderline high were treated? Because maybe, you know, within school, they don't even have budget to do anything to those on the border between.
Yeah, so we don't have, whether intervention is performed is not something we can track on the data, right? But what we can say is that the intervention, like assigning a high risk label does not lead to an effective intervention, right? So it could be the case that an intervention was performed and it had 0 effect.
Could this be related to what you were saying earlier about like very few people are assigned moderate label? And so your like confidence intervals around what happens for people assigned moderate are just always going to be huge.
Yes, it could be huge. So this is like related to statistical power, right? Like we don't have like a tiny confidence interval. Sure, it could be the case that the effect is non-zero, but it's definitely not a huge number. I think that's something we can rule out. Yeah.
Is the intervention that are required on students that are labeled as moderate risk similar to the ones as for high risk? Because you're saying like the checking on the margin between low and moderate would be even lower than moderate to high. So would you expect that the same amount of attention would be given to moderate students as high students? If you know what I mean? That makes sense as a question. Like, is the strength of the intervention the same for high risk and moderate risk students? So are they like comparable kind of experiments to make low to high and moderate?
Oh, I see. I see what you mean.
Yeah.
Yes, I think that they would be comparable interventions, but you're intervening on different students, right? So like, if, for example, you intervene on a student whose probability of graduation absent intervention is like 99%, this intervention, you know, you're upper bounding the treatment effect of this intervention.
Okay.
All right, so you would expect to see different effect sizes in the moderate to high risk comparison versus low to moderate, because these students look very different.
Okay.
I guess what's the power of the, so you say the effect is statistically significant.
Right.
But how significant in effect, so the graduation rates around that cutoff there are around 90%. How, so I mean, 1 in 10, let's say, you know, the dropout rate is 10%. How big an effect would you have been able to detect?
20%, right? So this is 80, so you could go all the way to 20.
What's the smallest effect you would have been able to detect? You're saying that you don't have enough data to say that this effect is significant, right?
Mm-hmm.
What's the smallest actually effect that you would have been able to detect here?
I'm not sure.
What the answer is 7%. So they've been at 7% effect, you would have seen it outside the interval.
But let's say.
So his interval width is 14. So having
I mean,
it
so
is
it's
7.
14. Oh, over there. Okay, but that's a huge right? So,
Yeah.
That's the graduation rates by a factor of 6, right? So,
And then this time maybe you can move on to something else. So the idea is that going back to the sorting algorithms analogy, it doesn't matter where we put students at the front of the list or on the back of the list. It seems like their graduation, the likelihood of graduation is the same. Right? So artificially changing someone's place in the list does not change their outcomes. So accuracy, there's no sense in which this high accuracy translates into like a high degree of improvement. So now we try to answer this question, like how is it possible that this due system can be simultaneously so accurate, yet ineffective? We propose this explanation based on the role of environmental features. Right, so we're claim that the graduation outcome of a student is conditionally independent of all measured individual information of that student once we know students' environments. All right, and get into more detail about this. So US schools in general, and Wisconsin in particular, are very highly segregated across school districts. So when you look at students who belong to the same school, all these students look much more similar than what you would expect based off random sampling of the statewide population. So from the perspective of on-time graduation, students in each school are basically identical. It's not that wrong to think that each student, like if a school has 100 students, it's really one student copied 100 times. All right? So once we know someone's school, it doesn't actually help us to know any individual information about them, like what their disciplinary history is, how many days they were in school, what their test scores were, in order to gain any more information about what their graduation outcomes. So this conditional independence statement is not something you can prove rigorously. We can try to disprove it, particularly test some of its major implications and see if they hold or not. And we'll see why this explanation can try to simultaneously explain the accuracy but ineffectiveness of the system. So one corollary of this independence statement is that if you predict someone's graduation outcome just using just using environmental features, and you compare the performance of that predictor to a model that uses both environmental features and individual features, both of these models will do roughly the same, right? Because like these individual features and graduation outcomes become uncorrelated once we condition on environments. So we can test this, and the statement's not exactly true. You do better if you include individual features, but you do not that much better. So you improve squared loss by around 10%. And here on the x-axis, I'm plotting like what is the marginal improvement in prediction you get from including any one feature on top of an environmental-based predictor. So we see things like attendance rate are like the most important, but each one of these things generally provides not a lot of signal above what we know already from the environmental model. So try to explain how this dependence statement explains both the accuracy and ineffectiveness of the system. So graduation outcomes and environmental factors are very highly correlated. So you can predict someone's probability of graduation just by knowing their environment. So if you plot the calibration curve, so these are models I train using the data that we have available. So one model uses all the available features and one model just uses the environmental features. And if you plot their calibration curves, both of these things look about the same, right? So there are small gaps, so you do get like a 10% improvement, but it's really kind of like, if you plot the curves, it's not obvious that these things are all that different. Yeah.
They're telling like one school like intervene on all the students.
Yeah, exactly. This is sort of where I'm going. Great. So this independence is consistent with high accuracy of who's graduating from school and who's not. And it also explains why the system's ineffective. So here I'm going to plot two histograms of graduation likelihoods for students in a specific school. So this is, when I came into this project, this is like what I thought schools would look like. So there's some x-axis that goes from 0 to 1. And here I'm plotting like what is the individual likelihood of graduation for students in that school. Michael gave a talk on, this is like nature's probabilities, like nature's P star. And then, so this school, say the average is around 80%. And I imagine that most students would have true likelihood around 80%. There's some higher performing students, there's some lower performing students. And the goal of prediction is to really figure out who is in this like red area, right? Like who needs help so we can intervene on them. But in practice, schools look like this. So either everyone has a high graduation rate or no one has a high graduation rate. There's like basically no variance in the within school district. So I'd like to emphasize this is for like a specific school. Like if you look at like variance across the state, there's a lot of variance. But all this variance comes from the fact that different schools do very differently. But once we look at each school, students look the same. Okay.
This is histogram of schools, or this is
the predictions for student in a specific school.
So x-axis here is a prediction. Not
yeah. So these are probability of graduation for students in a
based
school,
on your model, not the
based on the model that uses all the available features. Yes.
So this is for like a typical school.
So this is for a school I picked, but I'm going to try to convince you this is a typical school.
So if it was like a bad school, would these
this
bars on the right be more to the left?
This point mass would be here.
Interesting. Okay.
Yeah.
So this is based on all features, but your model or the juice model?
Oh, my model.
Your model.
Yeah.
Do
Which
you know
uses like,
any statistics about Dew's model? When also you look at Dew's model, prediction score has this phenomenon.
yeah, it's very similar.
You're saying good or bad? This seems like good, right? This seems like the model is functioning very well, like it's doing very effectively, which is opposite of what you're saying.
No, I'm saying like there's not a lot of variance in this distribution, right? Like it's that two people on the left are probably random noise. So let me be more clear about what I'm trying to say. So independence means that all students in a school have near identical likelihoods of graduation. So going back to this list, if two students belong to the same school, this means I should basically assign each student the same probability of graduation. Not exactly, of course, but like approximately. This is like a by and large statement. So any variation in scores within a particular school is basically random noise. For counselors that look at these scores, they find that the scores are like don't really match up with their personal interpretation of which students need help. And due to this disconnect, counselors just realize the scores are uninformative and ignore them. Right? So scores that are ignored can't have any impact. Hence why we see the system's ineffective. Yeah, Charlotte.
So in terms of the
intervention model, is it okay to like apply an intervention to an entire school, or is part of the problem that like within each school, these counselors are looking to apply it to the bottom like 10% or something, and when in reality it would be better to look at the bottom 10% of schools.
Yeah, so you're getting to my last one. So yeah, talking about, I have 5 minutes, all right. Great, so looking back, like taking a step back, like what does this mean about policy and like the impact of early warning systems more broadly? So it's exactly getting to Charlotte's question. So going back to the beginning of the talk, I mentioned that early warning systems really are about targeting, right? They're meant, the question they need to answer is like, who needs help? Right? A good early warning system should give me a very accurate answer to this question. And what we find is that there's, you can think about two allocation strategies, right? You can either try to intervene, rank all students in Wisconsin by assigning them individual likelihoods of graduation, or I can simply rank students by this school-based ranking, where I simply assign each student the graduation rate in their school, and then I do this kind of course ranking based off school graduation rates. And what we find is that due to this like statistical pattern that the individuals and outcomes are independent conditional on their environments, both of these sortings are basically the same, right? Like the individual allocation is like, it's not exactly no better, it's like only marginally better than just the school-based allocation. So the marginal value of prediction for this problem is kind of near zero, right? It doesn't actually answer the question of who needs help better than just taking an Excel spreadsheet and ranking schools by graduation rate. And to kind of give you a sense of how stark this is and how dropout prevention is really not bottlenecked by prediction, there's 5 schools in Wisconsin that account for 10% of all dropouts, right? If we're really trying to solve a targeting problem, there's very easy ways to answer this question of like who needs help that don't require any kind of sophisticated prediction tools. So the question really should not be like who needs help. This is actually a very easy question to answer. The question is like, it's clear who needs help, like what should the interventions be, right? Like how do we actually change things? And I guess one thing I want to kind of clarify is that this independence statement that I made, it's really just a statement about observables, right? It says like, this is something that's from the perspective of observed data, it's true. It makes no claims about what kinds of interventions are more effective, right? It doesn't rule out the fact that individual interventions or school interventions are any more or less likely, right? This is really just about focusing on this like targeting problem, which is what the prediction thing is trying to solve. Great, so I have some minutes for questions.
So you make an excellent point, and I think this is unarguable. But I'm wondering if you look at it, maybe one way to look at these predictive stories is for a school that where 80% of the students are tagged as high risk, it doesn't mean anything, right? Because it's not like if I focused on those 80%, the top 20%, I'm going to do anything different.
Yeah.
But for that other school that you actually did show us, where only 3 kids in the school were tagged as high risk, you can ask whether for those schools it does so. So this is not. You're right that the main answer should be this. Yeah. Still, if we want to also prevent dropouts in high-performing schools, maybe these school scores are effective there.
But if you have a school where everyone has a 95% chance of graduation, there's only 3 students that need help, it's very likely the counselor knows that.
You mean even without your scores?
Even without your scores, right? It doesn't tell you, like, I'm not bottlenecked in this high-performing school.
That's a different question of whether you're saying that this.
I'm saying, what's the marginal value of prediction, right? Like, how much better can I target resources if I use this system versus if I don't?
Well, if you don't use, and now you're saying something different. You're saying that I don't need to. I mean, I can't see the system to calculate because the school counselors can actually intuitively.
Because the makeup of students is such that this is a very easy question to answer, right? Like, there's basically either everyone needs help or no one needs help.
No,
and if no one needs help,
school where 3 kids need help, I need to identify those 3 kids.
I would be shocked if
time, maybe we can take this offline. Let's make this the last question.
Judy.
I have a question about like resource allocation, because funding is by school board, right? School district, but then this test is across the state. So I'm wondering, are you suggesting this because like the state will allocate funding for these, I'm sure 5 schools in certain school districts? right? Like, how does that map to like this mismatch?
Right, so where money is allocated is a highly political question, but at the very least, we should like know exactly this, like, we should not, fool ourselves or this question of who needs help. Whether you're gonna do something about it is something that other people will decide.
Okay, thank you. We'll
Yeah.
take the rest of the questions offline. Okay, the next talk is by